kind of selection or evolutionary operator. It depends how it works. In generally, for local search, we use individuals from one part of our environment. And for local search, if we use some kind of mating or selection, the individuals can mate only with partners from a constrained local neighborhood. A wide class of selection method is called overlapping population. I don't know why overlapping, but it is based on mixing individuals from both parental and offspring population. Maybe because somebody said that this population in this way overlap, but it's not an overlapping in fact because it's a stochastic process. So we can create offspring population and draw some individuals from parental. So for example, we take 10 individuals from parental population, and we have to decide because population size is constant. So we generate number of individuals for offspring population, and to add new individuals we have to remove something. So we have a choice. First, remove the worst. Second, remove a randomly chosen individual. And the last one, we can remove similar individuals. Very frequently, we are observing that individuals gather around some point. So we have plenty of individuals surrounding the bar and a few going to work. So we want to gain a variety of population. So we can add new individual which is far from the bar and far from work, but we have to remove something to reduce crowding. We can take some from the bar. So the most popular way of removing similar individuals is called gem succession. And gem succession with special impact on the crowd is called gem succession with crush. I will talk about it later and the way we do such selection. Finally, we have purely elitist strategy. So we take best individuals selected from the parental population. And the process of evolutionary computation with elitist strategy is very stable. We are sure that the best will survive. But population undergoes quick stagnation. So the best individuals will soon occupy all our space and will have no variety inside the population, and the only choice to get out from the elite situation is to use mutation with high probability to distract all species. Okay, this will be later. For the test, you need to know how the basic types of selection are processing the population. What's the difference between tournament and threshold selection? When to apply one? In which case? Into it. Questions? Okay, this slide shows you the most popular problem solved by the evolutionary computation. Traveling salesman problem. Who knows what's that? You. Okay. The idea is simple. Our salesman has to visit a number of cities. Each city should be visited only once, and salesman must economize on fuel. So we must find the shortest path connecting all cities, returning back to the original city. From mathematical point of view, it's a combinatorial problem. These cities are named A, B, C, D, E, or 1, 2, 3, 4, 5. And we have to find permutation of cities in such a way that the distance, the path leading through these cities is minimal. We assume that every city is connected with any city by the road. So the problem is simplified. In the real world, we have a net of roads, but this can be very easily added as constraint to our task. Now let's focus on the simplest problem. Okay, for the set of 5 cities, could you show me the best path for the traveling salesman from the city A?
For this case, you would just travel the boundary of the figures.
Just round.
Yeah, random.
So how much did you spend thinking of it? A couple of seconds. 5 cities. So the human can solve it very quickly. And if we calculate expense from the computer point of view, we have to do n times addition from n cities. And if we treat a problem in a random way, so we are drawing solution by solution, generating them randomly, what time is expected to find the solution? How do you think?
In that case, you would write something like all the possible solutions, combinations possible, and for each you will do addition.
Mm-hmm. Yeah, but it depends on our luck. We can find the best solution drawing for the first time, or in the end. So the time is not determined. Evaluation of a single solution is linear.
Yes.
So it's a polynomial. So we say that this problem is a polynomial complexity in a non-deterministic way. Now I'm going to show you how we evaluate, how we judge complexity of the problem. So this problem has non-deterministic polynomial complexity. The same non-deterministic polynomial complexity has the problem of
Yeah.
mobile network stations. Each station should transmit on the different frequency than its neighbors. So we can state the problem that each color cannot have neighbor in the same color. So this is the problem of the same complexity. By the way, this problem was initially solved by Gauss in the 18th century. So the history of the problem is very, very long.
So he tried this different colors for each country, right?
Yes, that's right. How to color the map. And the second problem is the problem of the bridges in the Königsberg.
Yes.
Is it possible to pass any bridge only once going around the city? So, based on that initial calculation, we can tell that algorithms have following complexity. So, first, algorithm with polynomial complexity, but determined. So we can say that after n square evaluation, we can have result. Then the problems of the class of the traveling salesman. Then there is a more complex class, NP-complete, where we are not able to evaluate its complexity, but a sample solution can be verified in polynomial time. So we are not able to prove that it has polynomial complexity, but there are some solutions which work in polynomial time. And finally, NP-hard, something which is non-deterministic. The function is evaluated polynomially in a polynomial way, but we cannot judge, estimate the overall time. And there are two graphs called Euler diagram. You know Euler. So he proposed it, and the state of art for the Euler's time is shown here. Simplest problem is polynomial time. Then non-deterministic polynomial, which overlaps with non-deterministic polynomial complete. And over it we have NP-hard. Now it is not assumed because we have no proof, but it is likely that all problems, polynomial, non-polynomial, non-deterministic polynomial and complete, are of the same complexity. And NP-hard are over it. So, what's the conclusion? That we can solve some non-deterministic polynomial problems in the same time as deterministic ones. If we have this, sorry, okay, I will have this slide later. So coming back to our traveling salesman problem, if we assume that for n cities we have n minus 1, it's not power, but sorry, a word is missing. We have so many solutions, so for 20 cities, 5 cities, we have 24 solutions, and for poor computer, we need 28 picoseconds. For 20 cities on the same computer, we need 77 years to process all solutions. We have exponential explosion of the cities. And 20 cities comparing, for example, to the number of cities in Poland to be visited by the transportation company, it's enough. But for example, in the USA, when you got 500 cities to be visited on a wide distance, you need billions years, not billions. Time of Earth existence is not enough to solve this problem. But these problems are now solved in a reasonable times. So let's say a couple of hours. But there are special algorithms. Okay, example of the traveling salesman problem for 100 cities. Evolutionary algorithm starts from random path. So you got something like here. Look at it and show me the best way. An idea? Could you show?
It's going from one to another, right?
Okay, but please try.
How are we supposed to go? Can you go like
Okay, let's go from left up corner.
left up corner?
This is right, but doesn't matter. Mm-hmm.
Yeah, so from down and from turn inside in a space.
Inside in
Spherical.
sphere.
Spiral, in a spiral.
Spiral
Yes. And then
could be, but I think that there is a better way.
Where do we
Anyway,
want-
I know the solution.
yeah, where do we want? Yeah. Where do we want to reach in the end? Or go away?
The same city, so no matter you choose. Let's start from here, for example.
Then we can go zigzag, maybe.
But if you go like zigzag, you pass this way many times. Is it not better to, for example, from this city, if you, let's say, go to this like this?
Maybe I'll try to
Yeah, go around the
calculate
circumference.
nearest neighbors.
Try to go to the nearest, but in some way. For example, we have groups. One group of cities to be visited during subtour. This. Okay, this three. This edge is to be passed by
So
once.
it's like I will compute the clusters.
Mhm.
So that whenever I visit any city belonging to that cluster, there my cost will be minimized a lot.
Yeah, that's right.
So
And
I will
then-
travel from cluster to cluster.
And then we add cluster to cluster. So we have, let's say, first cluster. Then we go here, second one. On the way we have to pass this city. And we have a choice. We can go there, but it's only one city. So we can pass this cluster. And I think it is better to leave this cluster to the
So what
return
we can
path.
do is, after computing clusters, we can travel to the clusters based on the cluster density.
Mhm.
If the cluster density is more, we go there.
So in general, it will go like that.
Yes.
Something like that, and return back.
Yeah.
So just looking at it, we need, I say, half an hour to find quasi-optimal solution. Evolutionary algorithm after how many? 10,000 of generation. Each generation with population of 50 cities. So many evaluation and final solution.
Yeah.
Is it optimal solution? Is it or not? How do you think? I think it's not optimal one. Because just looking at this graph,
You can go like this.
here,
Yes.
here we can go like this. This, and this, for
Yes,
example.
yes.
What else? This also could be modified because there are two choices. We can go up there and here. Maybe it is better, I don't know. But you see that the algorithm has generated a quasi-optimal solution. We can still search for more. And now go to the background. For traveling salesman problem, for any evolutionary condition, we have to state representation, quality function, which is the length of the tour, operators, selection method, which is mentioned, not mentioned on this slide, and some improvements, like local search methods. You said about clusters. So we can hybridize methods and search for clusters and then treat it as a local search method. Representation. Could you give me an idea?
Graphs where we have nodes and edges with weights. Weights are the distance.
Okay, but it should be coded for computer.
Yeah.
So I need computer representation.
So graph structure.
So in mathematical form, how can we code our graph of the cities?
Adjacency matrix.
Too complicated. Simplest way. We have 5 cities. How to show the way from city number 1 back to... So? Here, just an order. From city number 1, we go to city number 2. So in fact, it's a vector. City 1 first visited, then city 3, 4, 2. What is left? 5. So we go 1, 3, 4, 2, 5, and then return to 1. The simplest representation. Each number should be stated only once. So it's...
Would you actually count this as a representation? Because 1 might be connected to 2.
What?
Like the city 1 could be connected directly to city 2, and this representation doesn't give us that information.
We assume that every city is connected with every city.
Okay.
So we just show the path. For example, 1, 2, 5, 3, 4, So this is the coding for 1 goes to 3, then from 3 to 4, from 4 to 2, from 2 to 5, and back to 1. For me, it's this simple. Maybe I'm wrong, and it's better. Okay, so it is called TAF representation, integer permutation, and for this we have to generate variation operators. For genetic coding, genetic programming, we have mutation and crossover. Are they working? Do they work? Do mutation work for this representation? How mutation works? We change one number. If we change, mutate 3. It could be 1, 2, 4, 5. So let it be 2. We'll have 1, 2, 2, 5, 4. So it means that city number 3 will never be visited. So mutation does not work. Crossover. Let's take 2 cities. Will not, for example, 4, 2, 1, 5, 3. We split this, then we'll have first path 1, 3, 4, 2. Sorry, not this. We take this and this. 1, 3, 1, 5, 3. So crossover is not working too. We need new operators. Any idea?
We change one, mutation. If we change one value, we change the value that is corresponding to that. So if we change 3 to 2, we change the 2 to 3.
So we do something like that. If we want to mutate 3 and change it into 2, for example, we move 3 here and 2 on the place. Good operator. Anything more? It was a very popular subject
We can change the
in 1980s. So number of articles could be counted in not thousands, but 10,000, 100,000 during a decade. And after then came a catastrophe, I can say, because a heuristic method was designed which was able to solve this problem about 100 times faster than the evolutionary program.
Dijkstra?
But I am presenting you this subject because it's nice. We have a variety of solutions, many possible approaches. So, a class of operators called reordering operators. Remove and replace. Here we choose random city, random place of the city, and then we draw randomly second city, and we place one on the place of the another. Inversion. You said about it. So we, sorry, it's a kind of inversion. Here we choose 2 places and reorder the cities. So instead of going forward, we go backward in a subtool. Then we have displacement. We take a subtool and insert it in a different random place. So most of these ideas is based on the assumption that some part of the way is good, and we can just modify, start first from the city or later. Okay, finally we have reciprocal exchange, swap to cities, already mentioned. Recombination. Should we focus on the operators which preserve order of appearance. So we still assume that there is a cluster of cities which should be visited in the same order, and we protect that order. For example, 2-point crossover. We select 2 points and we copy middle paths from the first parent and remaining points from the second. But we preserve order. So, in this case, we take the basis here. Then we take 4-2 from the first individual, and we copy the remaining points from the second. So after this point we have 3. Then 4 was already used, 2 was already used, so we copy 1, 5. Order of the cities is preserved. Endpoint selection. Select endpoints at random from the first parent and copy remaining points from the second parent. So it's the same, assuming that we want to copy 1, 3 and 2. So we does 1, 3, and now we have a choice. These operators are very flexible. You can modify them. So we can add 2 after this, or we can give a place for a new city and maintain position. Later we take cities from the second. So 4 non-mentioned and the 1 is 5. This will result in the same as above. So 4 goes here and 5, so it's the same. It's a copy of the original. Anything more? Okay, we'll have next hour for the set of operators.